So, good afternoon to everyone from Europe, and also good morning to the examiners from the USA. And I'm Kiwei Wu from DT Electron. So I'm the chairperson for this PhD defense session. And so we have the PhD candidate Vladimir Dvorkin, and also we have the three PhD committee examination members, and also the PhD supervisors, including Professor Pierre and also Associate Professor Jalal. And a warm welcome to everyone who have the chance to join this PhD defense. And so the PhD project is about stochastic and private energy system optimization. So it deals with the stochastic optimal operation of the energy system wiring, ensuring the privacy preservation. And in the PhD defense, the PhD candidate will have about 45 minutes to present his work. And afterwards, we will have about 2 minutes break, and then we will start the Q&A session. We start with the examiners, and then the PhD supervisors will have the chance to ask some questions or give some comments. And then also the audience who could have a chance to ask questions afterwards. And so the total session should not exceed 3 hours. That's the maximum limit. We have to respect that. So I think that's kind of a short introduction of the PhD defense session. Now, Vladimir, you have the stage, and please go ahead with your presentation.
Thank you, Kiwei. So today I will present you the slides in the hope to lay some ground for a discussion, and I will try to balance the technical details and also give you a big picture of this thesis. And I will talk about stochastic and private energy system optimization. And before I proceed, I'd like to give a bit of motivation. We all know that energy systems is a transit from a fuel-based energy supply to renewable energy supply. And while it brings a lot of benefits, such as reduced emissions and affordable electricity supplies, it also reduces the degree of controllability in energy systems. And by energy systems, you can think of a physical infrastructure like this natural gas network depicted on the slide. And you can think of a system operator that optimizes operations of the systems. Its task is to supply every gas extraction point in the system while dispatching controllable gas injections and maintaining the pressures in the network using compressors and valves in the network. And what is interesting is that when all parameters are certain, the gas extractions are fixed and known, it's very straightforward to optimize this task and retrieve a solution. But the problem is that when these gas extractions are uncertain, then the system state also becomes uncertain. If you map uncertainty to the system state, you will see this picture where not all pressures, state variables in natural gas networks, can vary drastically throughout the day. And when we fail to optimize this uncertainty, we risk to drive the operations of the system beyond security bounds and also compromise efficiency of energy markets. The infrastructure simply doesn't work. And to accommodate this uncertainty, one needs to account for many factors. And one of them is the non-convex nature of energy flow equations. In power systems and natural gas systems, you can think of a pipeline equipped with a compressor, and the gas flows through this pipeline obeys the Weymouth equation, which is non-convex, includes quadratic terms and some sign conditions on the floor. And when it comes to uncertainty, when the parameters vary in the system, it's computationally intractable, this equation. And to improve tractability, the prior work uses certain simplifications or relaxations of non-convex equations in the hope that stochastic solution will produce meaningful real-time control inputs, which not always the case has been shown by prior work. It's also not only about operations, but also about markets and pricing energy under uncertainty. Deterministic markets, they are convenient because everything is certain and you know how to price energy and supplies based on fixed quantities and the marginal cost of production. But when it comes to uncertainty, a lot of things are unknown. For example, what is the cost of deliverability of energy under uncertainty, and whether all essential market properties will be satisfied. So thus one needs to think of a robust pricing scheme that ensures, and by robust I mean the one that ensures essential market properties such as cost recovery of energy supplies for all uncertainty realizations. And this motivates the first objective of this thesis is to develop stochastic control models with robust operational market performance guarantees for energy systems under uncertainty. As a second motivation behind this thesis is growing privacy concerns. To optimize energy infrastructures, one needs to collect a lot of data from the system, cost functions of energy supplies, demand consumption patterns, network topology, so on and so forth. As now more transfers of this data enabled, especially in real time, it's very convenient for a system operator because it can optimize energy system operators to cost and security optimal solution. The problem is that the data that is collected and utilized within operational routines tell us much more than we imagine. Take, for example, this load profile on the left and of some customer, and you can see that it consists in 3 periodic components, right? With some peaks, some variations in time, and this it manifests some sensitive data. It can encode a certain production technology of industrial consumer or some sensitive activity of residential customer, for example, electrical vehicle charging. And if you say that even if this data is not really available to any adversary, then this data still propagates to the system state. For example, state variables such as voltages, they are inverse to load profiles in the network, as we know. And you see that this load profile can be detected through the voltage measurements. And it means that a powerful adversary can reverse engineer the data even when it's not directly available to him. And we have a lot of real-time, real-life examples of real-time surveillance using power state measurements in the interest of commercial and private espionage. And to provide privacy for energy data owners, privacy guarantees for data energy owners, one need to think of a rigid definition of privacy. And differential privacy is one of those definitions. Specifically, it attains privacy for data sets as through randomization of the function of interest. You can think of a function M that maps real values to real values and consider its output result of computation using this function on 2 different data sets, D and D prime. And just looking at the differences between data sets, you can tell the underlying differences between data sets, input data sets. But if you add a carefully calibrated noise, a random perturbation to the output of the function, then you have a very interesting property. Statistically, the output of a function, of a randomized function on 2 different data sets are very similar. This means that when you observe a sample from one of the distributions, you cannot tell exactly from what distribution came from the one induced on dataset D or the one induced on dataset D prime. And there are 2 strategies to achieve this differential privacy guarantees for input data sets. One is the output perturbation method as depicted here. Another one is the input perturbation method when the data set is first perturbed with a random perturbation, and then the function is computed on a privatized data set. The problem is that these 2 strategies do not apply to energy system optimization. And the input perturbation does not apply because when we perturb energy optimization data sets, we cannot guarantee that solution of optimization problem would exist. And similar, when we apply noise to the output of a computation, we cannot guarantee that the perturbed optimal solution will be feasible for the problem of interest. This all involves unknown consequences to security of energy supply and market efficiency as we introduce noise to energy system computations. And this motivates the second objective of this thesis towards developing privacy-preserving optimization to provide privacy guarantees for data owners and performance guarantees in terms of market efficiency and security of operations for system operators. And towards the first objective of this thesis has 3 contributions. The first one is that we develop control policies to govern non-convex operations and markets of energy systems under uncertainty. So these control policies, they have two advantages. They ensure secure real-time operations, having some feasibility guarantees, and they extend deterministic pricing of energy to include the pricing of uncertainty. The second contribution is to propose a stochastic optimization of a fixed hierarchical structure to ensure market property satisfaction for all uncertainty realization. That is, the prices under uncertainty would satisfy the cost recovery of all energy suppliers for all uncertainty realizations and some other essential properties. And the third contribution is that we extended this framework to more realistic cases when energy market participants enter the market with their own forecast on underlying uncertainty, for example, with their own renewable forecast. And we provide market redesign solutions to produce a stochastic energy market that accommodates information asymmetry in the system. Towards the second objective of this thesis, I first developed adversarial models to reveal input optimization datasets from the outcome of optimization. And I did it to substantiate privacy goals for energy system optimization tasks. We then show that a lot of standard dispatch tasks are prone to severe privacy risk in the face of powerful adversaries using these models. And I thus propose rigorous a priori privacy guarantees for energy data owners by developing privacy-preserving optimization. This optimization takes arbitrary data sets within some specified domain, and it ensures that none of the items of the data sets will be disclosed as a result of using it within the optimization. And this guarantee is developed for distributed and centralized computations. And also to ensure that the system can accommodate privacy-preserving perturbation, I develop privacy performance guarantees to provide feasibility in real time to minimize the variability of a system state induced due to privacy-preserving perturbation, and to improve cost efficiency for some worst-case realizations of privacy-preserving noise. This thesis is built on 6 publications towards stochastic optimization of energy systems. These are 3 journal papers, and for private on the private optimization part, there is one conference paper, one preprint that is currently prepared for submission, and one journal paper. And today we'll talk about these 3 works. And if I distinguish between stochastic and private optimization part in my thesis so far, by the end of my talk today, I hope I will convince you that the privacy guarantees developed in this part are enabled by stochastic optimization methods developed in the first part. When it comes to optimization of natural gas network operations, one can imagine a graph that consists of nodes and edges, and every node is a point of gas extraction and gas injection. The system operator must make sure that all gas extractions are satisfied across all nodes in the network. To do so, it needs to find optimal dispatch of gas injections while controlling the system state described by flows and pressures. And it might use also some active pipelines equipped with compressors or valves to regulate the pressure and enable free gas flow in the network. And under the deterministic case, when all parameters are certain, one can formulate the following optimization problem to address this task: is to minimize total gas injection cost subject to gas conservation law that requires that all energy at every node must be balanced, subject to Weymouth equation that governs the flow of gas flows through the pipelines, and additionally subject to network limits to maintain pressures, flows, and injections within the network limit. What we know that it's a non-convex problem thanks to Weymouth equation, but we can solve it efficiently when parameters are uncertain. When parameters are uncertain, it's become intractable. And to overcome this obstacle, I consider linearization of the Weymouth equation. Specifically, I built a linear dependency between flows and pressure variables and compressor regulation rates. So essentially, I tried to replace this non-convex equation with a linear equation, where some linear sensitivity factors are retrieved from some stationary point when we solve this problem to stationarity. And what is interesting is that when I replace this non-convex Weymouth equation with its linearized counterpart, I know that the optimality condition of this convex problem amounts to the stationary conditions of this non-convex problem at the stationary point, which means that when there is not much variation in the system parameter, we can reproduce the solution of this non-convex problem solving a convex problem. When it comes to uncertainty, it's convenient to think of gas instruction as a random variable, given that has some mean quantity and random forecast error. And the system state in terms of gas flows and pressures becomes uncertain, so as controllable variables such as gas injections and compressors also become a function of uncertainty. And you can describe uncertainty by estimating distribution from historical data that's centered around 0 and have some covariance. And you can formulate the following stochastic programming to optimize the system under uncertainty, which minimizes the expected cost, subject to stochastic gas flow equations that requires the balance of every node to hold with probability 1 for any realization of uncertainty. So as the Weymouth equations is enforced here. And it's additionally subject to joint chance constraints that requires that the network limits will be satisfied for all realizations of uncertainty, but a small portion related to the small prescribed probability epsilon. And this problem is intractable because decision variables, such as this stochastic gas injection, is not specified as any function, is a function of uncertainty, but we don't know what exactly this function is. So it's intractable. To achieve its tractability, I propose to enforce a fine control policies for controllable variables, gas injections, and compressors. I enforce them as linear functions of random noise, such that stochastic gas injections has a certain mean and variable recourse, such that for any realization of stochastic of random variable, the system operator obtains a controllable control input for gas injections, and similar for gas compressors. And what I show in the thesis is that under this dependency of controllable variables on random forecast error, we can describe the state variables such as pressures and gas flows as a function of random forecast errors and control inputs, alpha and beta related to controllable injections and compressors. And this allows to achieve a convex reformulation of this stochastic program and optimize the system under uncertainty. Specifically, the joint chance constraint is formulated through a set of individual chance constraints. This is an example of the upper pressure limit. By using this affine expression, we substitute it in the chance constraint, and then we use unknown results to reformulate it as a second order programming constraint. Whereas the right-hand side is the deterministic part of the constraint that requires that the nominal pressure must be below the upper limit, and the left-hand side computes pressure standard deviation multiplied by safety factors that depends on the probability assigned in the chance constraint. So the less epsilon is, the larger the safety factor, so the more security margin you provide to satisfy this constraint. And what is interesting, when we reformulate this chance constraint, we also observe that this norm is a convex expression. This is a pressure standard deviation, and it depends on the controllable inputs, alpha and beta, on the decisions for injections and compressors. That means that we can formulate another constraint for nodal pressure variability and take this norm to put it on the left-hand side, and the right-hand side is auxiliary variable that retrieves the standard deviation of the nodal pressure. And then what we can do, we can use some penalty factor psi to penalize nodal pressures in the objective function for some value of the penalty factor. This way, we can trade off the expected cost of operations and variability of network state. And we can do similar for stochastic gas flows. And also, if you look at these equations, you see that these are linear equations. And we can invoke standard linear programming duality to price energy, to produce nodal prices for energy. But when we look at this coupling constraint, we see that this is second-order program constraint, and it couples control variables of gas injections and compressors. We know that we can take the dual solution associated with this constraint to extract prices for variability control. And for that, we invoke a second-order programming duality instead of linear program duality, which is similar to LP duality, with the difference that the dual prices associated with this constraints lie in the cone. And to show how it works in practice, consider a 48-node network where the blue rectangles show the points of gas extractions, and they are uncertain. They have a certain mean, and forecast errors associated with predicting these extractions has a standard deviation of 10% of the nominal value. By 3 sigma rule, it means that gas extractions can vary in real time in the interval plus minus 30% from the mean value. And there are some controllable units, such as compressors, injections, and valves, available for system operator to govern operations of this system under uncertainty. And when we optimize deterministic control policy, so we simply solve a deterministic problem, we see that we obtain a very small expected cost of operation. When we look at the chance constraint solution without variance control, we see that the deterministic solution is cheaper than the chance constraint solution because it's agnostic to variability and uncertainty. This means that the resulting variation of pressures is much larger than in a stochastic case. And it leads to the fact that in more than 50% of forecast error realizations, the system state is infeasible. So while stochastic solution produces stochastic control policies that govern system in a feasible manner, the probability of failure of an feasible control input is very close to 0. When we start penalizing the variance of pressures, we can trade off the cost and the variance of pressures. We can increase the cost with respect to the reference chance constraint solution, but reduce drastically the pressure of the variances. And similar, the variance of the pressure. And similar, we can increase the operating cost, but to significantly reduce the variance of gas flows. And you see that the main component that provides variance reduction in natural gas networks are valves that equipped in certain pipelines. And if you visualize all these effects, here on the left, you have a chance constraint solution without, which is variance agnostic, doesn't penalize variance of pressures and flows. And what you can see that system state is feasible. The probability of failure is very small, but it still can vary a lot within the day. And specifically, one can see that probability of flow reversal, indicated by these red quantities here, for certain pipelines is very large. And in practice, it makes gas flow unpredictable for system operators and poses some security risks. But once we start penalizing the pressure variance and flow variance, we achieve this variance aware solution that allocates all the pressure variance down to these 2 nodes and maintains a very stable operations in the rest of the network. And we're also able to reduce the variance of the flows to achieve a very predictable system state in real time. In the next part of my presentation, I will talk about privacy preserving optimization of energy systems. I will start with privacy guarantees for distributed computations of energy tasks. But before proceeding, I would like to give a definition of differential privacy. Consider an analyst that computes query over data sets. Query is nothing but a mathematical function that takes input data sets and computes some quantity. And consider 2 data sets, D and D prime. The one that involves includes some personal item, and the one that doesn't include a personal item. And when you compute the query on these 2 different data sets, you can distinguish the difference between the outputs of the query, meaning that you can detect the presence of an individual record in the data set. But if you add some random noise to the query output, what you can do, you can produce statistically similar random outputs of the function on two different data sets, D and D prime, which makes the data sets D and D prime distinguishable from the output of the randomized query. And this all formalizes by notion of differential privacy, specifically epsilon differential privacy, that states that probability of observing the same sample theta hat from randomized output of a function dataset D and D prime are similar up to constant epsilon. So observing the sample from the two distributions induced on two different datasets are very similar. And epsilon is called a privacy loss, and the smaller the epsilon, the closer these distributions one to another, then the stronger privacy protection you have. One can use, if this epsilon differential privacy uses Laplacian noise, one can use a Gaussian distribution for the random perturbation to achieve epsilon differential privacy. The notion that is similar to previous one, but it allows some small probability of failure, this little additive term here. It reduces conservatism of the guarantees. And I first applied this framework to distributed energy system optimizations. In many cases, they are solved in a centrally manner. There is a system operator that knows all information from the energy graph, like all supply functions, all loads in the nodes, and then it computes cost optimal solutions and solves the problem. But it's always not the case, because in many applications of interest, such as optimizing the entire system of the European continent, it cannot be solved centrally, because there are a lot of independent system operators that do not like to share their data, their local data sets. Instead, what they're doing, their process can be mimicked by distributed optimization to solve their local optimization problems without sharing any data, but then they coordinate on a single solution related to voltage variables at the adjacent nodes, right, between the two systems. And what we know about distributed optimization, that they enjoy the glory of privacy preserving, because one doesn't need to disclose all the data, only certain variables as a result of local computation. Let's take it critically and see whether these distributed schemes can provide some privacy breaches. So let's consider local optimization of this graph as follows. We have some local data sets, for example, this datum, the load quantity at this node, and over iterations, we need to release voltage variables related to these two nodes. So one can think of the local optimization as a single mapping from a load quantity to two voltage angles at these two nodes, right? So, but one can also think of adversaries that solves the opposite problem. So it takes voltage angles released by a system operator and then maps it back to the load quantity that was used in computation. What I show in the thesis, that this vector of privacy attack is viable. So there exist two problems, two attack models that can solve adversarial problem. Is a tracing attack that relies on the repeated observations of voltage angles to infer this load quantity. And there is a more powerful privacy attack. It requires a bit of more data, but one can use a certain empirical risk optimization problem to outcome the load quantity from a single observation of these voltage angles. And to provide privacy guarantees for distributed optimization, what I do in the thesis, I use a notion of beta adjacency of load data sets. So consider that this quantity D belongs to a data universe calligraphic D. And to provide privacy for this quantity, I would like to make it indistinguishable from any other load quantity D prime, which is differ from D by at most beta, where beta is non-negative coefficient. When beta is close to 0, these two quantities are almost the same, but as you increase beta, you require more indistinguishability level for quantity D. And to obfuscate this quantity, to make it indistinguishable from D prime, when we release these two voltage variables, we can take the local computation and add some noise to its output. So to compute voltage angles and add some noise. And the key result of the paper is that when I calibrate this noise to Laplace distribution with zero mean and scale beta over epsilon, where epsilon differential privacy parameter, then the local optimization of this graph achieves epsilon differential privacy. That is, when we compute these voltage angles on a data set, on different data sets, since this problem is now randomized, the output distributions on different data sets are statistically similar. And to see how it works in practice, one can think of a large power system that is split into areas, and system operators of every area perform their local computations, and they only exchange voltage variables related to adjacent nodes, while they keep all local data for themselves. And we can solve this problem using standard distributed algorithms. But what I show in the thesis is that they are prone to privacy breaches, specifically when required no indistinguishability of any load value in the system from the release of voltage angles. Then an adversary can compute exact load values. And in this example, it's just 3 selected loads in the system. When we increase adjacency level, so we now would like any load in the system be indistinguishable from any other load in the radius of 10% from the nominal value, adversary will observe a single sample from the resulting distribution of voltage angles. So, and as we increase adjacency coefficient, you see that the variance of this distribution increases, and the probability that adversary will receive a single sample that is close to the mean value is very small. So, which means that that's how the privacy guarantees are provided in practice. In the rest part of my talk, I will talk about centralized privacy-preserving computation. And if the distributed one was more related to high voltage grids, I will talk about distribution grids now. Distribution grids are solved. You can think of distribution grid as a graph of a V3 topology where every node has a load, local generation, and the system state is described through currents or flow or power flows that flow through the edges, and voltage state variables specific for every node. And when we optimize this grid, ideally we would like to solve optimal power flow problem, to find such a solution for generation that produces the least cost for the system. And so you can think of this optimal power flow problem as a mapping from load data sets to state variables. For example, from this load quantity to this floor in this edge. What you also know that when we have a change of this load, it directly translates to change of flows, right? So it's directly exposed activity of the customer connected to this node of the distribution grid. And you can visualize this problem as follows. You would like to minimize the dispatch cost as a function of this power flow in this edge. And this edge belongs to some visibility space, right? The optimal solution to this problem is placed here, and to decouple like information about activity of this customer here from the release of the optimal solution of this floor, what you would like to do, you might use output perturbation methods to provide differential privacy guarantees. So you would like to randomize add some noise to optimal solution, but you will end up at that the probability of obtaining a feasible solution is at most 50% in this case. So it means that you need to find an alternative solution, F2, that is suboptimal with respect to F star. But when you add a calibrated noise to its value, you will see that it will remain within the feasible space of the problem with very high probability. And so this perturbation of this sort provides not only privacy guarantees as a result of randomization, but also feasibility guarantees. And the main question is to how to compute this nominal solution F, whose perturbation is safe for arbitrary networks. And to answer this question, we propose a perturbation strategy for distribution OPF problem, where we would like that a floor in every edge would have some mean component and random component. Right? The problem is that floor is a state variable. It cannot be controlled by distribution system operator. Instead, distribution system operator can control the generation. So, and to ensure that the flow is randomized with at least parameters of with this random perturbation, one needs to increase generation in the upstream part of the network by Xi and reduce the generation in the downstream part of the network to compensate for this perturbation in the upstream. In this case, this perturbation is equally compensated for by the 3 generators in the network. And to provide this randomization policies for arbitrary network, we formulate it as a following affine expression of random perturbations. So where generation at every node has some nominal mean component and some random component. And this alpha is a decision variable to be optimized. So you see in this example, the response to perturbation to upstream is equally allocated among generators, but sometimes it might not be cost optimal. So that's why we model alpha as a decision variable. And we enforce specific constraint on this decision variable. We would like that all perturbation from the upstream part of the network will be compensated for by generation in the downstream part of the network. And when we take this generator policy and map and substitute it into ACOPF equations, we obtain the following affine function for power flows that consist of a nominal component and a random component that depends on this perturbation. So, and you see this, you can already sense the connection to the first part of the thesis, where I use this affine policies to accommodate data uncertainty. The very same way I can use affine policies to accommodate random perturbation used to provide privacy in energy systems. And I can also formulate a chance constraint optimization to optimize these policies in a feasible manner. This problem takes this affine function variables as a affine function of a random perturbation and minimizes the expected cost, subject to power balance constraint that must hold with probability 1, and subject to constraint on grid limits that must be satisfied with probability 1 minus eta, where eta is very small probability of failure prescribed by system operator. And to the work floor of this method is the following. A system operator specifies the parameters of the random perturbation, and then it runs chance constraint optimal power flow problem to accommodate random perturbation in the network to optimize affine policies. Then it takes a solution of the chance constraint problem where these policies are now optimized, and it takes a sample from the same distribution to produce a generation control signal that would produce a privacy preserving solution for power floor, but at the same time, there is a very high probability that the sample will be accommodated in an energy network. And what I show in the paper is that we can calibrate the parameters of this random perturbation. Specifically, we can choose this covariance Xi, where every diagonal element depends on the beta adjacency parameter and on epsilon and delta differential privacy parameters, such that when we output energy flows currents, then they're randomized sufficiently to make input load vectors indistinguishable from the outcomes of the randomized optimal power flow solution, right? So observing the same outcome f ahead from a data set induced on some vector d and d prime will be very similar up to epsilon and delta privacy parameters. And how it works in practice, you can consider a 15 bus radial distribution grid with 14 customers. And we assume that we can fully observe the system state of this network. And consider that there is a customer located at this node 7 is very atypical load pattern that consists of large, medium, and small component. It's depicted on this graph on the left. So, and assume that it encodes some private information of this customer, some production technology. And what we, if we look at the solution of deterministic optimal power flow problem, we will see that the power flow in this age directly exposes this load pattern. The power flow is depicted in this plot here. But now to obfuscate this information, when we release information about the power flow, we use the notion of epsilon differential privacy on beta adjacent flow data sets. And when adjacency amounts to 0, it means that there is no privacy guarantees, all information is leaked. But as we increase adjacency, you see that now the power flow is randomized in this age. And if it's small enough, you achieve the following effect. You hide the presence of this small high frequency variations, the smallest periodic component here, but you do not obfuscate some other information about medium component and the two large disturbances in the system. To hide those two, you further increase adjacency coefficient. Here, for example, you hide both the high frequency periodic component, medium frequency periodic component, but you can distinguish the presence of two big disturbances in the system. And when you further increase adjacency, you basically passes on this load profile to optimum power flow problem, but your output is basically a white noise. And it's also will be feasible with very high probability. So this sample trajectories of power flows, they come from certain distribution. And this, if you visualize it, the distribution of a power flow in this age as a function of input load quantity that can vary using beta distance, you will see that the distribution, blue distribution induced on the original load quantity and those induced on adjacent load quantities are similar up to epsilon and delta parameters. Fix epsilon to 1 and delta probability of failure, fix it, for example, to 75%. Then what you will see that these distributions, they differ from one another to some extent. But as you reduce the probability of failure to, let's say, 7%, then you align these distributions obtained in different data sets. And when you observe the samples from this distribution, you cannot tell what load quantity is used in the input. And it's very similar for voltages at node 7, when you compute them on different load quantities, you see the differences if privacy parameters are large, but you can strengthen the privacy properties by reducing the probability of failure to closer to 0. And in conclusion, this thesis presents several concepts. So the first one related to stochastic optimization of energy systems, and it offers stochastic control policies to accommodate uncertainty and variability of uncertain renewable energy sources or uncertain energy demands in a secure way. It also offers extensions for the stochastic energy pricing to price uncertainty and variability. The same methods of stochastic programming are used to enable privacy guarantees when we optimize energy systems. So for both distributed and centralized computations. And these guarantees, yes, originated at the interface of stochastic programming in differential privacy. And this affine dependency on the random perturbations that I explained before allows not only for privacy properties, but also for feasibility guarantees and some performance guarantees for the system. And if I'm asked what the impact of this work, I would say that resolve privacy concerns in energy systems would encourage many things, specifically OPF-based dispatch practices and distribution grids. It will also facilitate engagement of privacy cognizant energy users as long as they have insurance that their data will not be exposed as a result of interaction with the system. We will attract more users to participate with the grid. And it will also encourage transparency of energy markets and operations. And the current work that was motivated partially thanks to this thesis is that I extend the stochastic policy optimization to a case of multi-stage actuation of control policies. So specifically in the paper, in the thesis, I assume that uncertainty within the day or some fixed amount of hours is described by a single mean quantity and standard deviation, ignoring this temporal evolution of the stochastic process. When I bring control policy optimization to multi-stage case, the system operator will be enabled to create control policies as more information about uncertainty reveals, and to produce more available cost and variance trade-offs. And on the private optimization side, if in the thesis I mainly focused on solving linear programs privately, I extend the concept to solve second-order con programming and semi-definite programs to this privacy preserving, to solve them in a privacy preserving way. One specifically can think of this famous maximum volume inscribed ellipsoid problem, that you need to find an ellipsoid will be contained in some closed polyhedral space. And we know that solution to this problem unique, and it means that the radii of this ellipsoid would disclose the parameters of this set. It means that when you will add noise to the radii of this ellipsoid, you will risk produce a solution where ellipsoid is not contained within the set. And in some control problems of interest, it might pose severe security risks. So what I propose right now is to sacrifice optimality of this problem, produce an ellipsoid with a slightly smaller volume, but I know that when I will perturb the radii of this ellipsoid, it will contain within the this space with a very high probability. Thank you for your attention, and I'll be happy to take your questions.
Yes, Vladimir, thank you for keeps timing. And so I think we could have perhaps 2 minutes break, and we will start again 6 at the CET time. And yes.
All right. Thank you, Gavin. As you wish.